Excellent. So want to just lead that we're here, that Unit 6 is probably one of the most important. It's really meant to be the culminating unit. So you can just see that we did have a slow start, just acknowledging that most students don't come into high school ready for um, to perform at the level of the NGSS, which is really meant to be assessed at the end of 11th grade. So that's not a total surprise, but you can just see more and more performance expectations as we go. And Unit 6 just has a lot of them. So really one of the most important units. We've even come to say it might even be worth, if you feel yourself getting behind, really shrink Unit 4, maybe even Unit 4 to the end of the year to allow you to have time for Unit 6. Probably, again, Unit 5 and 6, I'll just quickly say are, this students already know about forces and energy quite a bit, but they don't know a lot about waves, and they don't know a lot about electricity, power production. And I think they know some of the climate science, but they are oftentimes really hungry to learn about climate science from their science teacher. They're just getting a lot of different information sources, and we just hear that they appreciate it, learning it from their teacher. There is a Unit 7, and we have that webinar coming up after the workshop. That one, though, really, for instance, I've already done 2 of these. So that's 3 small little lessons. So we did one before winter break, and we did one at the, in actually, for me, it was actually the beginning of semester 2, just because it was a situation where I was going to have a sub, and that pairs pretty well with a sub. So those are meant, they can be an end of the year. It's great. We've done it. I think last year we did it at the end of the year, and it's a fun way to end the year. But just know that Unit 7 really is meant to be flexible. If you got 2 days before spring break and you want to keep the class going, that's an option for you. I'll give a little peek just of the big picture here, and then turn it over to Matt to walk us through the calendar. But this unit kicks off with students being tasked with creating a 50-year energy plan for the state of Oregon, where they start off reading actual documents from the Oregon Department of Energy. Also, it's worth saying that this unit was supported by the Bonneville Environmental Foundation. So really beneficial. They connected us with power industry people. They didn't directly connect us, but supported us in connecting with the Oregon Department of Energy. So lots of real world feedback from people. And then also, again, this now is several years old. I don't know if it's 5 or 6 years old. And yeah, it's got to be at least 6 years old. So we've gotten a lot of feedback from teachers to make improvements too. So it has really gone through its paces and gets a lot of positive feedback. But again, we can always improve. So really do appreciate hearing that feedback. Okay, so they get tasked with that at the beginning. And then we got our first activity, which is Voices of the World, where they read excerpts from people around the world that are affected by power production and climate change. And then because we have some physics targets for them to learn, and I'm not going to do this for every one of them. I just want to show that maybe here, develop and use a model of 2 objects interacting through electric and magnetic fields to illustrate forces between the objects and changes in energy of the objects due to the interaction. All right. One of the most beautiful things that shows that is a speaker. That's an electric motor. And so a speaker, you put in electricity and motion comes out, sound. So that's just a great connection to Unit 5, our waves and technology. And everyone likes making speakers. We just had the in-person workshop in Newport, and just a fan favorite. And I saw Patrick mentioned it as one of his favorite things as well in this unit. So super crowd pleaser. And then we rip those apart and make electric guitars. And that's just pretty awesome too. So, but we can't power the world from electric guitars. So we need to figure out, how do we make generators that can produce the kind of scale of electricity that we consume as a society? And one of the fastest growing power production means is wind turbines. So that just is a really nice fit, and it's a great engineering project. We'll say that we've made it the patterns approach, and that's a common one that a lot of people have done. All right, and then also because the other fast wind turbines and solar power are the two fastest growing, so we wanted to get a touch in both of those. Solar power offers a great chance to add a new mathematical model. And then at this point, I skipped it, but I know Matt's going to go over almost the same thing again, but with a little more. I'll just say that they looked at some economic and environmental impacts at the beginning of the unit of each power production means, but we haven't talked about the climate impact of the power production. And so the storyline brings us naturally to talk about climate science and all of these earth science targets. I'll just read two of them. Well, one for the whole unit: analyze a major global challenge to specify qualitative and qualitative criteria and constraints for solutions that account for societal needs and wants. That's the whole unit. And then if we look at one about the climate science that I was just talking about, very straightforward right here, earth science target: use a model to describe variations in the flow of energy into and out of Earth systems results in changes to climate. So you can just see the storyline really weaves together really nicely all these different performance expectations. All right, so once they have a feel for the climate impact of the different power production means, and also learn some of the earth science around climate for going all the way back to paleohistory, then they put it all together and do our final new type of computational thinking. This unit, they don't do any coding themselves, but they use the computer to rapidly calculate the impact of different energy mixes. And again, we're going to show all of this in the webinar. So that's kind of the webinar in 3 minutes. I'll turn it over to Matt to round out some of the things I went a little light on, and guide me where you want me to be on the calendar, please.
Yeah, I think from here we'll actually we'll start at the beginning there. Like there's this arch of how we unroll this unit and unravel and look at it. And so what we want to do in our aim is we want to start and end with thinking about people who are affected from climate change or have a solution, things like that. So that is looking at the Voices of the World activity. If you're new to patterns, the patterns approach and patterns physics, we won't go through the whole calendar, but this is kind of an example of what you'll see. There's a task and some narrative, and then below all of the resources that you need to make that successful. And so this is one that is loaded with so many great interactives and links. And this is one that we are going to start with. So let's actually dive in and take a peek at Voices of the World, just on that next tab over. So in Voices of the World, this is one we started day one. We want students to start looking at a unique perspective of lots of different people from a variety of places all around the world. And this is adapted from a climate change tea party by Rethinking Schools, which we've linked there. The ideas and some of the characters are from Oregon. So, for example, this is Ed Edmo, formerly of Celilo Village. Did I pronounce that right, Bradford?
Yeah, I believe.
Yeah.
Of course. Yep.
And so we are just looking at different people who are somehow affected by power production, climate change, might have a solution. And these people are from locally, but also all over the world. And this students take on the role of this person. And with the climate mixer, if you go to the next tab over, they are introduced to this, and they basically start in big groups. And in my case, I normally do like groups of 10 or 12 to start, and then people share who their person is, where they're from, and the students need to find somebody who, who's being affected by climate change, or somebody whose story involves a connection between water and climate change, all of these different people. And so this is the intent and goal is to start with people in mind. Who are we talking about? Who are the people who are affected most by this? And just get students talking. And I found students are really engaged with this and really like take on those roles, take on the responsibility of representing that person. And it's one that really does go quite well as students are engaged in looking at that. And yeah, then I'll hand it off to Bradford. You want to talk about the problem statement and looking at the resources that we have.
Yeah, excellent. Thank you. Yeah, so table of contents, we always encourage students to look through the whole thing a little bit. Here is the Oregon 2022 Biennium Energy Report. And of course, it is 2024, but they do not have that report out, and actually probably won't come out until 2025. So this is the most current report out of the Oregon Department of Energy. And you can just see that there's a couple, Yep, I don't want to get lost into this, but they read an excerpt. It's just a couple pages long, and it's mostly graphics. But again, original resource materials here. So just good stuff. Again, reports back that, that's a good, students find it interesting. And, again, you can just see this is really cool. I'll show this. This shows every power plant in Oregon. So you can just, find your school, and you can zoom in, and you can just see, I mean, these are small little, wow, there's more here than there was even a little bit ago. And of course, here's the larger dams on the Columbia River. And then of course we got some wind power up in the gorge there. So this just generates high interest. It's an easy thing to actually get students to read. Okay, so they read that, and then here's that charge to be the Energy Plan Commission. So also, I think most people have heard of it by now. And again, we even had to update this because a few years ago, it was just off of coal, and now new law has Oregon needs to be able to, on a typical day, be off of fossil fuels. So that's the Clean Electricity and Coal Transition Plan, which has off by fossil fuels. Technically, they can still have natural gas for times of high peak demand. All right, so that from there, they got to make their problem statement. And we didn't read it too closely, but it's very important that in those performance expectations that students come up with constraints and criteria. And constraints are very, that's straight out of the reading. So again, one of those constraints is you need to be completely off fossil fuels by 2040. The criteria, there is an opportunity. This is very leading. We have this is super leading. And but that partly is in that background research section, you can just go with whatever students come up with. But that final project, we really do need it to be along the lines of economic, environmental, land use, and climate impact for the coding to work. And for years, we tried to make it variable with teachers so that they could put whatever criteria people came up with, and that no one was using it. And it was a lot of work. So in any case, now that we are steering students toward, or most teachers want the pre-made computational thinking at the end, it's important to have these three. So if anyone was passionate and you wanted to go with a different one, that is modifiable, but that is a little extra work on your end. All right, and then just to round it out, we always start with that wild guess and then end with a data informed prediction, and we'll do the same thing with the energy plan. So again, that kickoff includes an initial 50-year energy plan that they mess with, take a screenshot and paste over this sample one that's right here. Gonna quick check that I hit everything that I wanted to. Yes. All right.
Yeah, so this is one where, students are aware of those trade-offs, and lots of that comes out actually in this slide that Bradford has up, the driving question board. And we just want to make sure that that's clear. Students are looking at this idea of this, power system. And so in this modified driving question board, we've added a little bit more guidance this year, what expectations we want from our students, and we really want them practicing modeling being a big part of this. In this case, they're going to be modeling a power system, a system that is created by us. And so they are going to be thinking about tracing the energy of the power system, from charging some electronic device, starting from the energy in the battery and work backwards through that power system. And so what steps are needed to happen? So we have them out on this this whiteboard. If you don't mind clicking to the next slide. And then, what questions do they have? We know students are filled with curiosity and questions, and so we ask them with a red marker, what questions do you have about that system? On the next slide, Bradford, we ask them, how might we judge how good this is? And this is like that basis of that criteria and constraints, or those criteria. I'm sorry, those criteria where how is it costly? Is it taking up a lot of land? Does it have a climate impact? That's really kind of leading them to come up with, how good, how might we judge how good our power system is? And lots of times students are coming up with those three criteria on their own. And then of course, we want them to share out. And so they're going to be coming up with, presenting a question, connecting there. We fill up a idea or driving question board, have them write questions that they have on a sticky note, oftentimes like a unique question in one per group. And then we just have them share those questions out. And a lot of times those good questions lead to more questions. And we are able to answer lots of those throughout the unit as we're looking at that. So overall, this, again, the starts, it's really looking at big picture ideas. And then we're going to be taking those and starting to dive into those ideas a little bit more. And I think we'll do that here. Bradford's going to talk a little bit about finish up driving question board, but also talk about background research.
Yeah, excellent. And this came before students would do the criteria in the portfolio. So that's just, it shows another opportunity for to have that come authentically from the students. And then of course, here is that one I already mentioned. So again, they're coming up with the criterion, but if you want to utilize the pre-made structure, which again, we have found over and over again, students come up with those three, maybe slightly different words. And we actually, why did we choose like cost versus economics or financial impact? Because it's a shorter word. You'll see that in the last, we just need short words to fit in the cells for the computational thinking at the end. All right, so here's the background research. So students go to this website, Student Energy. It's actually all done by students, although in collaboration with adult experts in the field. In any case, you can just see that just every energy source is here, and you can click on it like, oh, geothermal. Whoa, sorry, my screen's blinking for me, so it's probably blinking for you quite a bit. You can click on geothermal, and it's just really nice because each energy source has a video, it has a short reading, it's just manageable. So then I'll hop back right there. So that's it. And if they even want more information, they can go further. But in any case, so you jigsaw this, and there's a couple different suggested ways in the slides, but you'll just make it work in your classroom. And these are currently in the order of the existing, in the order of how much power they supply to Oregon. So hydro is the biggest, coal is the second. Although we don't have a coal plant in Oregon anymore, the last one was closed. We have coal by wire, and that coal is coming from Idaho and Wyoming. That coal power is coming from there. Okay, so they go and they have a description, and then they talk about the impact on those three criterion.
I think one thing to add, and then Bradford, I'll let you talk about that, is when students are doing the research on that student energy, and they're looking at the different different energy sources, they're looking at it in you know, with those contexts in mind. So there is you know, looking at it in terms of cost, the environmental impact or land use, the climate impact. And that allows them, that gives them some background knowledge and some examples to use in their writing. And we have our students actually after day 2 or day 3, after doing all that research, we have them write the first paragraph of a 5-paragraph essay, which we'll nod to and mention more at the end with some of the extensions that we have. And those letting them have some examples and seeing the examples with that that student energy map really helps. There are some that are missing, and if when you look at the key, so sorry, let me take a step back. On that resource, there are videos and writing, and basically the videos and the writing cover the same information, which is really nice. There are a couple things that are missing, and on the key, which we can show later, it has blue and red, I believe, and one of those colors indicates just that it's not, that information's not there, that you might need to like have students do a little bit more research or help students out with those things that aren't in there. And this is just a great opportunity to get students sharing that information. And you can see here, you know, the additional information that might not come out straight from that piece. So it really sets that stage for that. Students also are coming up with their most important criteria of the 3: land use, cost, and climate impact. And this helps them get a little bit of more context before they make the decision for themselves. So just wanted to give a little bit more context to that, and I'll hand it over to Bradford to talk about how we introduce the ideas of electricity and power.
Excellent, thank you. I might stop my screen share to make my image bigger. And maybe I'll do that spotlight. Okay. This is just a really nice one, although I think it's even more fun with food coloring. So if you put just a little bit of red food coloring in one bucket and then put like a lot of blue or green or whatever color in this one, then students walk by, and this is the battery, and you have a real battery. So sorry, I should have slowed down. I kind of had that slide up there for a little bit. You set up students play with wires, light bulbs, and a few other things, just kind of seeing some stuff that they might have done in middle school, but we just find it really depends what their middle school experience was. So some students have it, some students don't. And we just want to have that common background. So it is a battery, 2 wires, and a light bulb lighting up. And then students are going to act out that circuit. And I don't want to go back to the slide, so I'll show the slide after I complete this. As they walk by the battery, they fill up their beaker with a little bit of water, and it's a certain amount. And this is symbolic. Each beaker is an electron. And if it has energy in it, that's a electron with voltage. So the energy per unit charge, but let's say for this what demonstration or acting out, that the energy per electron, and then as they walk past the light bulb, that energy in the electron is transferred to the light bulb, and then of course it also flies out into the room. And it's a great, I'll switch back and share my screen. That is a great, there's just so much good stuff in this. So this would be the first one. And if we, so as soon as you touch the wire, all of those electrons get energized. And so they all have, that's of course high voltage. And students get this. We don't start with words like high voltage. We start with words like water in the cup. And so the packet graphic organizer for this starts students realizing, okay, they do know this is energy. We have done a whole unit on energy. They know energy flow. They know that batteries have energy, and that gives energy to the light bulb. So some of this you orchestrate like these slides suggest, and then students start to see that, okay, as time goes on, no surprise, the battery gets drained and more light goes around. And there is just so much good stuff. If the students spill, that is symbolic too of the resistance in a wire. That energy gets spilled in the demonstration. And of course, that could be representing the heat in the wires. We weren't going to show the packet, and so maybe I won't, but the packet does just walk them through saying, hey, what did the water represent? Oh, that was energy. What did the students with the beakers represent? Okay, that's electrons. That path that we were walking, ideally you can even put down tape. Oh, that represents wires. So it's just a very approachable way to figure it out. And voltage, which can be a scary word to freshmen, but simply put, it's the energy per electron, energy per unit charge, Coulomb, joules per Coulomb. All right, so they can get it. And, in the demonstration, we later come back and hook up like 2 batteries or a 9-volt battery, depending on what light bulb. 9-volt battery will burn out most light bulbs, so you got to be careful with that. But they get it that if you scoop up more, if each electron has more water in it, that is, or actually I'd say it this way. Sorry. We put the question to them. How should we change the acting out based on the fact that there's a 9-volt battery and the light bulb got a lot brighter? Oh, would more electrons come into it? They know that you got to get more water over there. And we could either have more electrons, but it's the same wire. So it's not like electrons would just poof into existence. So then it really is, the electrons must be carrying more water with them. Yes, high voltage. And the other thing that they can do is they can also move faster in that circle, also called a circuit. Okay, so that's a little bit deeper. That's about the right level for the webinar. And so in any case, you can just see that students act out the circuit, and we build up, straight out of strategies for English language learners, benefits every student, that we're not giving them these technical words and having them look them up in the dictionary. So they act these things out. And again, this is something that we get a lot of positive feedback that, oh yeah, voltage, energy per electron, no big deal. Current is electrons per second, which can be affected by how fast they're moving, in addition to how many electrons there are. So most of the good stuff of electric circuit basics get there in just a 20-30 minute activity. Even have them graph it.
Hey, we should just have it be like an
Good, thank you. And of course, we walk the triangle, right? Here's a picture of the real life battery circuit that they've made at their desk, and you have one running during that app. We got the graphical representation here comparing different voltages and what's happening with the energy being transferred per second. And then of course, we have some mathematical representations. and don't want to overdo it, but yeah, it's no surprise. This is an equation they already had from unit 3, that the energy transferred per unit time, how much you transfer each second, is it 1 cup of water per second times 6 seconds? Yeah, no surprise. The energy transferred would be 6 there. And it's very useful for us to, of course, again, power is defined as the energy transfer per unit time straight from unit 3. Okay. With rounding that out, I'll just say some nice posters to have kept. Oh, there's a little update there, but we want this. This is going to be an important thing for high voltage power lines, that the power is going to equal, I'm going to say it in terms of the analogy. The current is how many electrons are passing the bucket per second, right? So charge per second. And then the voltage is how much water. So what's the power per second? Well, it's going to be the number of cups times how much water each cup has. And nearly every student gets this. So ends up being really good. And we can just see that if we double the voltage, the power is going to double. Or likewise, if you double the current, the power is going to double. And of course, power and current can interact themselves. So that's something that we explore later. And then I did say it, so I'll just show the slides that does. So here, let's repeat with 2 AA batteries and predict. And I do it right on the fly. The students right on the fly while they're acting this out, come up and do that. And this is just a nice little GIF of a FET that can be showing these things. So here again, 1 battery, 2 batteries. And if you have the FET open, you can check the voltage there. So it's just a nice little, again, we're doing the triangle. We got something happening in real life. We got graphical displays. We can use that FET as a diagrammatic display and our equations. All right, with that, I will hand it back to Matt to see if I missed anything and then take us forward.
Yeah, thanks, Bedford. Bedford, if you don't mind while I talk to get your video sharing settings ready. So one kind of big thing is that, this is that introduction to power, and they're gonna get some tangible usefulness. Of course, they're up and moving around, and there's lots of thinking going on. But when they get to wind turbines and when they get to solar cells, they're going to use energy versus time graphs from a sensor, and they will get to that proportional line out. And so those connections keep on coming up, and that reminder of what power is and where it comes from, energy transferred per second, will come up again as power. So that's a good one. This also sets them up for thinking about speakers and how speakers work, what is going on with speakers and this. So I'm going to let Bradford talk about and then show this video. But the big idea before you go talks is, the big idea is we can take motion and we can generate electricity. We can take electricity and we can generate motion. And so going back and forth, the whole concept of this activity is all centered around that. And so I will hand it to Bradford, and I think and let him talk about it a bit.
Yeah, this is excellent. We will make these in the workshop. I left the speaker and the electric guitar in my garage, but we that didn't have the amp. But here it is nearly magical. You heard it, several people already say that this is just a really fan favorite. Look at that. It's just a cup, a wire, which the video will do a close-up on here in a second, and a magnet. So it is that simple. Students can make them in 10 minutes. And then, of course, we have a design lab around them exploring, getting at those performance expectations of looking at how magnetic fields and magnets can interact and transfer energy. But here I'm going to hit play and then I'll make it large screen. You'll hear the speaker just for like the first 2 seconds. I don't know why we didn't do that a little bit longer, but and then the video will explain the rest. But when we first play, and I'll rewind once. So it wasn't very loud, but you could hear the speaker.
Okay, here we have a speaker, which is really an electric motor. We're using electricity coming out of our player, going through a wire, and I have a permanent magnet for it to push off of. A speaker is a motor. So if we run this backwards, this is electricity into motion. If we run this backwards, we should get motion into electricity. And then of course we'll do electricity back to motion with this speaker. But let's check and see if I can make a microphone, which is a generator taking motion into electricity. 1, 2, 3, 4, 5, 6, 7.
Okay, good.
3, 4 speaker. But let's check.
So there, I'll just pause there. That is just a meter of copper wire called magnetic wire, not because it's magnetic, but because it's good for making electromagnets. I just like to always say that because it says it's magnetic wire and then students think it's magnetic. It's actually, copper is not magnetic, and but it's good. Really thin copper you can wind really tightly, so it makes a good electromagnet. All copper, wound, all current will make a magnetic field, but that's a particularly strong way. The same amount of current will produce a stronger magnetic field if you wrap it in that solenoid. Okay, we actually got another video because this one was the speaker into a microphone. Again, speaker, electricity into motion, a microphone, motion into electricity. So that's a generator. And that's a very simple one that students can build. And it's just so simple. Why not do it? And then students have hand constructed the.
Check and see if I can make.
I want to go to the next slide, but here, and then here, this is the electric guitar. Again, this is a $3 electric guitar. So it's not the most amazing thing. Definitely strongly recommend borrowing a amp from the band. Most high school bands now have amps. So if you have a big amp, it makes it a lot easier. We've done it for years with like a 15-watt amp and it works, but it's more finicky and you got to really, sometimes you do everything right and it doesn't work and you bump a wire and then you play it again and it starts to work. But when you have, this is a 500-watt amp, it just works every time. So if you're able to get your hands on a 500-watt amp, hopefully from the band, that is a really great resource. So again, that was acoustic just for that split second. This is the guitars that they make at the end of Unit 5. And again, you can just see orange juice jug, 6 nails, 6 different weights of fishing line. Again, $3 guitar here. And then I'll play it.
Oh, you got it's supposed to be.
Okay, here is the magnet. We got our coil sandwiched underneath.
And I'll just say, so that's that same coil ripped off the bottom of a speaker, jammed underneath the orange juice jug, so that I'll zoom backwards, so that as this, as the string vibrates, that moves this piece of wood, technically called the bridge, because it's bridging the strings to the orange juice jug called the soundboard. But as the spring vibrates back and forth, that pushes the wood up and down, which moves the magnet closer and further away from the coil underneath. And I'll play the video to show all of that.
We got our coil sandwiched underneath there, and just 2 wires going into our.
Yeah. Okay, so that is just really fun. Obviously, making an electric guitar from scratch is something that students definitely remember and launches us. It's a lot easier to get students to talk about the physics of generators when they've made a generator, especially when that generator is an electric guitar. Okay, so let's look at some of the how the packet supports this. And I'll zoom, or where I'm in the key. Well, here's the speaker, and I'll just show that here in the first cartoon, we got the permanent magnet. That was that silver magnet that we saw, neodymium. Those are strong magnets, but you saw how little that was. That was not like a giant magnet or anything. And then we got the wire, but because at time 0, there's no current, there's nothing happening. If I actually go down to our energy bar charts, right? Energy is a cross-cutting concept, so important. And here with the skills in unit 3, we're seeing that happen. And then once electricity at time 5, electricity is now flowing. We have a current. And so we have this dotted line. Students can hand draw this in. That's the electromagnet. And we can see in this case, it's North Pole, North Pole. So those two are going to repel. And so the speaker is going to get pushed forward. Also, we can take a peek down here at our energy flow. And oh yeah, some of the battery's been used up. There's electricity flowing. And because that electromagnet is being repelled by the permanent magnet, we have kinetic energy. The speaker is now starting to move forward. And of course, at 10, the current goes to 0. And then at 15, the direction of the current flips, which flips the direction of the electromagnet. And students can see this when they're playing around, right? There's a whole day of them playing with magnets, wire, and their speaker. And then they see now, oh yeah, north and south, it's attracted. And so the speaker gets pulled backwards. All right, and then this is the generator, which again, it culminates with them making the electric guitar, but it's hard to see what's going on, right? It's really hard to see that motion of the bridge moving. So that's why we suggest the FET. And field lines are nice. Voltmeter is also nice, but you can decide if you want those, if they're a distraction, or at some point they want to turn them on. And they just see that most students think that it's the magnet right next to the coil. And that, of course, doesn't do anything. And so really it's technically a changing magnetic field. And what's the easiest way to change the magnetic field? Move it closer and further away. So a changing magnetic field technically makes an electric field. And of course, if you have electrons in the presence of an electric field, then the electrons start to move. And of course, that's called a current. But in any case, moving a magnet near a coil wire creates electricity. That's excellent. And there's a couple different, students have a hand crank generator, they have the FET, and then also the electric guitars. So that all culminates in, of course, we want to assess them on their understanding of using the big ideas of science to explain phenomena and solve problems. And there was that design lab. So also here, then again, though, there is that assessment on use the big ideas of science to explain how speakers work and generators work. And of course, checking on their ability to represent the energy flow in those. All right, so that I think I hit most of the highlights, but I'll throw it back to Matt to just check in.
Yeah, this is just a good opportunity for students to use energy again as that big idea, cross-cutting concept. One of those ideas that are called out throughout and really helps them kind of connect those ideas together. Also, just a fun time for them to interact and see that in motion there. So those are all ideas there. We are going to take a little bit of time with Fredford, if you don't mind going to the agenda, to just take some time to check in and get you talking with each other. And we kind of intended this with some thoughts in mind. Is like if you what excites you or even concerns you about teaching electricity, magnetism, and climate science this way. I know that oh, I just realized, sorry, my video is off. Uh, uh, what excites you about that? What concerns do you have? If you're maybe new to teaching or new to teaching physics, what are those things that you might need to brush up on? They are using this Faraday's law FET. There are different levels of knowledge that could go along with that, and so we just wanted to just give some opportunity just to talk with other educators that are around the state and around the country as well. So we have some breakout rooms set up, just random breakout rooms. They might be 4 or 5 depending. And how long do you think is good, Bradford?
Yeah, we were thinking like 6 minutes.
Yeah.
I think still
Good.
sounds good. Yep.
Yep. So 6 minutes, and we will they'll close and just give you a 10-second warning here as it comes back. So we'll put the prompt. Bradford, do you have that prompt copied?
Yeah, I will in 5 seconds.
Okay. Again, the prompt is introduce yourself. What excites you and or concerns you about teaching electricity, magnetism, and climate science this way? Obviously, we're not all the way through the unit yet, but we'll start with that. Again, we'll see you back here in 6 minutes, and see you then.
I have a tickle in my throat. I'm gonna just grab a cup of water. I'll be right back.
Okay.
Excellent. So we are talking about scaling up. And so that, of course, has several pieces to the puzzle. With that, again, here is original documents from the Oregon Department of Energy. And they're really great. You can play these forward and see over time how things have changed. A lot of really neat stuff. And the one that I wanted, which was actually that map I showed at the beginning, right here. And of course, why do where is power located? Okay, no surprise. It's oftentimes located where we have giant energy sources, and that's not always where everyone lives. So we can see there's a lot of power generation right here in the Columbia River Gorge. But we got to get that power from where it's generated to where people use it. Okay, so invite some we got some pieces in the slides about, what would a generator look like? And there's some great videos, but what I wanted to go over with you, I gotta find my tab here. No, it's not the one I wanted. This is where they use the big ideas of science to explain all of this. But really, I wanted to go back to that power equation is current times voltage. And, it's not a surprise that power loss is also current times voltage. And so if it is current is how you lose energy in wires. So of course you want the smallest current, but you got to deliver that power. So if you're going to have a small current, then you need to have a gigantic voltage. So students are led in a learning arc that makes it pretty intuitive. They usually beat the teacher to the punch of figuring out, oh, you have high voltage lines. So you can minimize the electrons and the bumping of the electrons in the wire, spilling that water as they move from the Columbia River Gorge to where that power is being used. And it all, again, comes together with them using the big ideas of science to explain large-scale power production, distribution, and the grid. All right, so that one is kind of simple, but a really nice step for the storyline, and it gets into a couple things that we really want students to have a basic idea about before they leave high school. So returning back to our, actually, I don't have a nice, well, here's the packet, but again, maybe you can start to fill in the learning progression that students would be drawing in as they go. But our next piece is we made those electric guitars, we got generators, we have a piece of the puzzle that, okay, once you make that, those wind turbines are in the Columbia River Gorge, and now you got to move it to where people live, could be Hood River, the Portland metro area, all over the place. So a lot of Oregon gets some power from that. With that said, that then launches us into the engineering aspects of wind turbines, and I'll hand it over to Matt to talk about that.
Yeah, so we're going to go through kind of two learning arcs, like looking at wind turbines. And we often talk in class, and as Bradford was talking about, like that, how do we get the power to us? There's lots of videos in the slides of different types of energy sources, geothermal, wind, hydro. And in those cases, often, or all of those cases, we are taking some sort of motion and converting it into electrical energy using a generator. Then after this, we'll talk about solar, which is done in a very different way. So, we'll talk about the need for that. We'll look at, geothermal plants, all of those big ideas. But we harness, we hone in on this idea of the wind turbine. And so this is a little slice of engineering that students are doing. Students are tasked to create a wind turbine at a local park. And they're required to do a mock-up of this. They'll have some data, they'll look at the challenge. And again, this is like a slice of engineering. So students are tasked with that. Students then are also tasked with providing data for others in their group. And this is kind of what Bradford has up. These are obviously, these are teacher made, but students make these as well, where students are trying to create the turbine that makes the most power, while making trade-offs of a certain budget, which we'll show in a bit. And so they are encouraged to take data on one of four different ideas. So power versus angle of blades,
Matt.
Versus number of blades, shape, and area. Yeah, go ahead, Bradford.
Yeah, sorry to interrupt. I did bring them, so I will stop the screen share and just quickly show this, because this is oh, thank you for doing that. All right, so students come up with the same things over and over and over again. Like, it's the size of the blade, the angle of the blade, shape of the blade. Okay, great. So we used to be like a 2-week engineering project, and that just took too long. People then didn't get through the rest of Unit 6. So now strongly recommended is pre-make the blades. And so you have, if they always come up, shape, angle, size, number. So at first, have all of the blades for that initial exploration already made. So students just come, I have here's the tower, the Kidwind Tower. And since the blades are already made and this group is doing size, they plop it on, and you just literally kind of friction fit it. You push it in and it turns, and I'll just show there's an energy sensor that's on the supply list, and it's beautiful. Right in graphical analysis, you get the power output in watts. So then students can take a data point in 2 minutes. And then they pop it off, they put this back up, and then they grab the next size down and put that on and take data. So now they generate data on those 4 questions in 1 day. we really aim for the first day. But again, if it's the first year teaching it, maybe it's a day and a half. But again, just want to show that they can get their own data on a single parameter, which is science. How does the size of blade affect power? That's a science question. And then I'll throw it back to Matt so that he can round out the engineering aspect of this project as well.
Yeah, so they are tasked with that, providing that data. When they get the data, of course, we want them communicating and presenting. And so we have students present their data as well on a whiteboard. And this is again, data that's provided, but we want students to provide that data and give their recommendation. So they have to listen with intent. In the packet, they are looking at and creating a graph of other people's, and they are explaining the graph and reasoning about what is the best recommendation. And there are trade-offs. We have cost trade-offs. For example, we put, and it's going to be too much to go into now, but a price on the number of blades. Each blade that they create costs more money. And so while you can see on this graph, 6 blades might be the most power output, it also is twice as expensive as 3 blades. And 3 times more expensive than 2 blades. And so they have to make that trade-off between number of blades, the area, the shape. There's no trade-off for angle. And so whatever optimal angle your class gets, students that should be an obvious choice for them. Now, it's okay in class if your data does not look like this. That could depend on lots of different variables, but we want students using the data to make their best recommendation. And so they are able to communicate that and look at that. And again, we call this a slice of engineering. They're kind of doing this project within. We have them write about it, use the claim evidence reasoning format to come up with their best solution. And then, of course, we want them to also use their creativity as they get their base solution. If they want to go and adapt the shape, adapt different aspects, maybe looking at how far out the blade is. There's lots of different variables that they can change and do given the given time. And so really hands-on. And I'll hand it back to Bradford to kind of finish that off and look at our next data collection.
Yeah, excellent. Matt said it, but I just want to say it again of that, this example right here, power output versus area, it really does just keep increasing, but you do see that typically a little bit bigger, the power drops off. That usually is the fact that there's a very uneven wind coming out of the fans. And so how you take your data, the fact that the really big blades are so big that they have part of the blade is outside of the windy area of the fan. And so you will see this drop off. That's why we decided to put this as the exemplar. So most teachers will see a drop off, but if students are careful during the creative phase and make the shape of the blade such that it stays in the wind zone of the fan, they'll just see bigger is more powerful. Yeah, excellent. So that is the talk science. So each group is an expert and they talk science, and a little bit of just a repeat, but just to emphasize it, because this is what we call the patterns approach. Then because of cost, just what Matt was saying, you got to figure out trade-offs. And so then you got to talk engineering. They use data-informed design decisions. So they're making the decision about their blades and angles based on data. And then, of course, they can get creative and do all the things that the pre-made blades didn't do. They can twist them. They can move the blade closer or farther from the axis, all that good stuff. Okay. Yeah. That wraps up, and that's a pretty full engineering project. That one has multiple days. There's some infographic information. There's an excellent video, and we're doing pretty good on time. It's definitely one we're going to show in the workshop, but I think maybe we'll show this here because it just is so good. If you haven't, we get the question a lot, and we were fortunate that we got to work with some engineers that worked on wind turbines. But here is just, I think, one of the best videos, and it's just a couple minutes long. So I think we have time. I'm going to stop share and reshare in video mode.
How did we get from this to this? In some ways, the answer just boils down to climate change. We need way more renewable energy, so it makes sense that lots and lots of engineering.
Sorry, what was that?
It was not showing on my screen.
Oh,
It might have been to the wrong tab or
yeah, I do wonder. Okay, so let's see. I think this is right now. Can you see it?
Yep.
Yep, cool. Good. And yep, we'll play it here in just a second. Yeah.
How did we get from this to this? In some ways, the answer just boils down to climate change. We need way more renewable energy, so it makes sense that lots and lots of engineering and economic resources have gone into improving and enlarging windmills. But while climate change can explain why windmills have pushed towards really good design, it doesn't explain what makes a design good. I see three main features to explain: the size, the number of blades, and the shape of the blades. Size is easiest. The bigger the area, the more wind you can use, and therefore the more wind energy you can capture. Plus, the higher up you go, the less the wind itself is impeded by stuff on the ground, the faster it blows, and therefore the more wind energy you can capture. So for a windmill to have access to air with a lot of energy, it should be giant and tall. However, a paradox of windmills is that they need to capture energy from the wind while also letting the wind pass. If you extracted 100% of the kinetic energy from the wind, it would stop moving and there'd be nowhere for incoming wind to go. So you have to let some wind through. Calculation shows that a mathematically ideal windmill can only extract 59% of the wind's kinetic energy. Since windmills can't block the wind too much, they're faced with a trade-off. Either have fast-moving blades that cover a small amount of area, or slow-moving blades that cover a large amount of area. This is because just as an airplane wing produces more lift the faster the plane is moving, a windmill blade catches more of the wind the faster it's moving. So roughly speaking, a fast-moving windmill, like modern ones, needs correspondingly fewer, thinner blades in order to not slow the wind too much, while a slow-moving windmill can have more, wider blades. Obviously, modern windmills have gone with the narrow, fast approach. So why are modern windmills designed to spin more quickly than old windmills? I mean, if slower were better, there would be no reason modern windmills couldn't look like giant high-tech sails. The answer comes from Newton's third law. Just as the wind pushes the blades sideways to turn them, so the blades push back on the wind, giving the air a reverse twist and hence some rotational kinetic energy, which is energy the windmill doesn't capture. So the most efficient windmill will give the wind the smallest twist possible. And you guessed it, the faster a windmill blade moves, the less rotational energy it gives to the wind. This might seem a little counterintuitive, but a similar thing happens when a ball falls and bounces off of an angled block. If the block isn't moving, conservation of momentum and energy mean that the ball bounces to the left and the block gets pushed right. But if the block starts off moving to the right, it's able to absorb more of the ball's energy when it accelerates. The faster the block moves, the more energy it extracts from the ball. You can see this because the ball moves less each time. Windmill blades are a bit more complicated, but it's roughly the same idea. For decent efficiency, a windmill blade should move through the air at least 5 times faster than the incoming speed of the wind, though obviously different parts of the windmill blade are moving at different speeds, and so the shape varies along the length of the blade. So, in summary, an ideal power-generating windmill is big to capture a lot of wind, tall to capture strong winds, fast-moving to be most efficient, and narrow-bladed because a fast-moving windmill needs to have a smaller blade area, aka just a few narrow blades, to not slow down the wind too much. This video is
Excellent. So that is, I want to just point out how so much of what we do in the wind turbine project captures that, right? So where you how high up you put the wind turbine affects how much air it captures. That's one reason not to collimate the air coming out of a fan. If you really want to make a fan produce a very constant, even wind, you can put a grid-like structure made out of cardboard in front of it. But real earth wind is not consistent. It really does matter where you put a wind turbine. So we kind of like leaving the fan as is. And then during that creative phase, students that discover it or certainly design for it get a very positive feedback, increased power production from it. So just a really great, that is a full-on 3-day, 4-day engineering project. And then going to our next project, which is really small. It's really meant to be 2 days. I'll say the first year it's going to be 2 full days, and it's always kind of fun because you get to go outside. It's a slice, so it's just a really on it. Yeah, it's really meant to be 2 days. So again, depending on how much time you have in the year. But again, yeah, obviously you could spend more time on it, but to put it to you a little bit fun, let's actually do the same thing we do with students and just ask this question. Here's the phenomena. Why are solar panels, solar cells, mounted differently? In that lower left is a picture of solar panels in the Galapagos Islands on the equator. In the middle there is a installation near I-5 and 205. A lot of people might be familiar with that in Oregon. And then, totally different. Look at Alaska and look at those. And those ones that we're looking at in Alaska, yeah, are like that. And just for fun, the webinar really isn't meant to have too much, but I don't know if it's worth showing, but the other real neat thing that we do with students is to give them solar panels and the earth, little earths, and every one of them figures it out. Oh my gosh, yeah, in Oregon, especially on the equinox, we're at about 45 degrees if you laid it flat on the ground, and no surprise, you tip it back so it faces the sun. If you put it down flat in Alaska, and look, if you can see my video, that would, if the sun is coming from over here, it would barely get hit. So you got to turn it back to face the sun. All students figure that out, and it kind of spreads like wildfire in the room. Once a group, oh yeah. So that is awesome. That's just a really cool thing, especially because of what I'm going to show next. Good. Is that, and we'll spend a little more time on this in the workshop, but here is some typical data collected by a student during that day. And they just wiggle. It's just fun. It's not amazing fun, but it's pretty good fun. They just wiggle this line in Desmos. And of course, this is a sine function. And with a little bit of wiggling, students figure it out. And now, of course, what's going to happen during the data discussion. They have to make sense of that. There was 3 constants. There was a B, and a C. And it's really cool because they do figure that out. They don't learn everything that they learn in math class about sinusoidal. Some teachers see this and go, I have to teach students sinusoidal. No, we actually just teach this blue curvy line that mathematically fits the data. And of course, yes, I would strongly encourage you to call it a sine wave, but I do want you to think about just approaching it, that this is what we've done all year. We've made a mathematical model act the same as something in the real world. And this is data they collected outside with the solar panels. Pretty fun. And I got off the wrong tab. I don't want to overdo it. Kind of lost where I am in the packet. Oh, I was on the key there for a minute. And so we give them the data from those 3 panels that they already saw on the equinox, and then they put in their image where they took, because obviously in a given day, you can only get so much data about your state. And so in any case, they compare it to the Galapagos, Oregon on the equinox, and Alaska and their own data. And students figure out so much of this all on their own, of course, with the help of the graphic organizer. And then, of course, write it up. And that's, their final lab of the year. So it's just a nice touch that it shows a new pattern. So for the whole year, we've just had those 4 patterns. And technically, Unit 7 introduces inverse square law. And then this lab introduces sinusoidal. And again, I do want to, I guess you have to trust me a little bit that sinusoidal can be tricky when you try to talk about lots of things from math class, arcsine and ratios, but that's not what we're doing. We're using it as a mathematical model, and they get it that if you rotate a solar panel 360 degrees, you're back to where you started. So we need a mathematical function that rotates 360 degrees and is back where you started. So much of that just is intuitive, and it just really shows the value of the patterns approach, that most students are not intimidated by that and are able to make sense of a lot of that. And then, of course, with teacher help, we see that they're pretty successful. All right, I'll toss it back to Matt to just round out anything on the solar panel, and then take us into the deep dive on earth science and climate science.
Yeah, thanks, Bradford. Can you go back to just the agenda really quick? Oh, I guess I want it. Yeah, calendar. So, big idea. Let's start where we started. We looked at how people are affected by different climate ideas. We did background research on how power production is made. We made speakers and generators to look at that side of large scale power production. We looked at another piece of the puzzle, which is solar cells. And finally, we need to learn a little bit more about climate science to get this idea of how what we do with large scale power production affects our Earth. And so that is kind of the intent here. Bradford had a slide up before that blue slide. Again, blue and green slides are intended for this teacher. This is just some background research that you may want to read as you're going into this. It's short, gives good background information for about climate versus weather, and then about global climate change. Just a good resource for you if you are interested, just to get some background of what's expected there from students. There is kind of also a note in the slides if you go to the next tab over, Bradford. Yeah, just we do some time looking at climate versus weather, and looking at timelines. So and we just wanted to call that out. There are lots of slides and good resources that probably don't make it quite into the webinar, but are worth looking at and going through, looking at these interactions, these complex interactions between climate and weather. And so just wanted to call that out there. When we're for the bulk of student activity is going to be kind of in 2 different places. This is something that was kind of born out of that pandemic. That there are resources in the packet, but there's also resources in Desmos, and just kind of looking at the 2 there. We're going to show you one, and just kind of get that big idea for you to get those ideas over. So yeah, Bradford, do you want to add anything before we go into the Desmos?
Yeah, no, just that there is a ton of valuable slides here that it doesn't make sense to go through in the webinar super quick, but you'll want to review them, and there's just a lot of good information there. So just want to leave you with that, including the answers for the Desmos activity. So we're about to hop into the Desmos activity, but each page in the Desmos activity has a corresponding teacher slide that you likely would want to show to students as they work through that.
Nice, thanks. Yeah, so yeah, if you don't mind opening that Desmos, it takes a little bit to load. On mine it did at least. So this is the Desmos that we have. Students are encouraged to play with a complex simulation on this page, which we're not going to show, and look at the many factors. And then we're going to look at a simplified, a good but simplified model of what the Earth system is. So I don't think worth showing there. There's a link to a more complicated one, but really the base idea is if we are thinking about a warming planet, we are having more energy in than out. And so we're going to label our graph or our simple climate model with these 5 different ideas. So students get that idea, and they're actually able to compare 2 different models. They'll write out on there. They're looking at a simulation model and then the Desmos model as well. And just to get some of those ideas down of where's the energy coming, where's the energy going. Then they're asked to kind of play with the simulation. And so if you click on one of those black dots, you can drag them up and down, and you can see that changing the Earth system changes, either creates a warming climate, it could create a climate that might be in equilibrium, or you can also change it to create a cooling climate. And so we are just asking students to notice and wonder, what causes a warming climate? What causes a cooling climate? Go ahead to that next tab. So we want to, of course, summarize that. They're going to create a warming climate. They're going to summarize how that is. They're going to summarize a cooling climate, and then there's a slide that goes along with that. And the next slide, Bradford, if you don't mind. Yeah, so big ideas. In a warming climate, the Earth gains energy because the energy in is greater than energy out. Cooling climate system as well. So that's kind of the basis, and then the rest of the activity is students wrestling with a given situation and wrestling how to represent it in a variety of different ways. This is encouraged to be like give the situation, have students try to create what they think is representing that situation, and it gives them the liberty to play around with the simulation or the model to get that there. So in this case, or I also wanted to call out that the different situations that are given are specific, are put in here specifically because they were called out by the NGSS. So one that we want to start with and we also want to end with is how does increased CO2 in the atmosphere affect that? So we've had conversations about greenhouse gases. There's good videos that we've watched. We've looked at another simulation that shows the interaction between infrared light and CO2. And so students are able to modify this. If you were to grab one of the red arrows, Bradford, and drag it down, and they might represent increased CO2 in the atmosphere like this, where it's no more energy from the sun is coming, which is a big misconception that you probably will see. Students will just grab a energy arrow from the sun and bring more energy from the sun. No more energy from the sun is being created. No, where's that energy coming from? It's energy that would have escaped into space, coming back down to Earth. So they represent that. And then we'll just go one more slide here, Bradford. what this slide does is takes their information from the last slide and has them explain, does this model show a warming or a cooling climate and why? So the rest of the activity is really lots of presenting an idea, a challenge, having students play with the model and the simulation and explain their thinking. What did it cause? Why did it cause it? Why is it warming? Why is it cooling? Again, warming and climate cool, it's specifically called out in the NGSS. We want to start with the ones that are most important and then look at lots of different scenarios that could be possible along the way. Yeah, and I'll hand it off to Bradford if you want to add anything or go from there. I think there's one more slide that you might show too.
Yeah, excellent.
Yeah.
Yeah, I think that covers it pretty well. Again, there's, the 10 situations called out for in the NGSS. And so there is a slide for each of those. And again, the answer key, so to speak, is in the slide deck, which would have this same scenario with the notes and references to the framework where they discuss it. So that's good. That's a good, a good 1-2 day activity. And from that, then students are able to, again, from that all the way back to that student energy, put the pieces together to figure out the climate impact of different energy means. Here we just, again, there's I was going to say there's an embarrassing amount of slides, but really that's that many resources. So here again, here is just each of those slides that we were showing. And then here's a little bit more advanced picture. We had showed a very simple picture and, what do you notice? What do you wonder? And it's a good conversation piece. And then of course we do want to make sure that students know the paleo history or recent history and paleo history of CO2 in the atmosphere. And that is, that's using our tools that we've done over and over again throughout the year. They're inner scientists. So we're seeing a graph and then we're thinking, what is happening in the world based on that graph? And of course, we got several of those graphs, famous hockey stick graph. And so it goes through all of that. That completes that picture. And of course, then we have, we want to assess and give them feedback. We want to understand where they're at and give them feedback on where they're at using the big ideas of science to explain the climate science of the Earth system. Okay, so yep, you can see there's some light touch on nuclear energy and philosophical chairs element of that. And that's been really interesting. I've, you already know this probably about your students, but there are students that have really taken it on themselves to learn about climate science outside of school. So that's, it's a nice chance to have that philosophical chairs discussion. All right, and then to zoom out, again, Matt did this last time, but one more time. We started with needing a 50-year energy plan for Oregon, and we did that. We did the engineering portfolio, read original resources, voices of the world. To get that physics, we did the motors and generators, scaled up to wind turbines, the slice with the solar panel, then looked at the Earth system and the climate science. And now we can finally put it all together. I see there's an update and make our 50-year energy plan. And okay, it's just doing a time check. So this, want to show it. So starting your 50-year energy plan, I don't want to, again, in the workshop, we're going to have you make one. And we even, I think we might have you open it. It's just, it takes like 5 minutes before you know what to do. but I just want to kind of walk you around the app. And of course, there are slides for this, and we just get feedback that to show a lot of slides in the webinar can be overwhelming. So sometimes, but it is nice to show slides sometimes because we have these call outs. And again, you don't have to show these slides to your students. This just helps you know. So we have
Reverend, and maybe just I would start on slide 324 to just give the big context again.
Yeah, nice. Good call. Thank you. So maybe I will turn this into full screen. All right, let's review, right? We have this problem statement. We as the Energy Plan Commission seek to create a 50-year energy plan that must address the energy needs of Oregonians for the state of Oregon. The constraints, and there's more than this, but these are the really good ones. And we got 4, meet the energy needs of the state for the next 50 years, stay within the projected growth each decade. That is also a way of bringing in the economy, right? So you can't change too much in a decade because that would cost too much. And then provide reliable power. This is really cool. We got a lot of positive feedback that students that have gone through this and been fortunate to be able to bring out like Bonneville Power administrators, Bonneville Environmental Foundation, and students presented to adults. And they gave us feedback multiple years that students, after doing the 50-year energy plan, understood that if you go all wind, you have to build energy storage along. And I'll point that out, but I just want to show how much this all fits together. And then, of course, be off fossil fuels by 2040. Whoops. And then the criteria was that environmental impact, land. We just did land because it's 4 letters. So land use, climate impact, air quality, and then startup cost and maintenance, economic impact. Cost is just 4 letters. So we in the spreadsheet, and this is a screenshot of the spreadsheet, and I want to stay here for a little bit longer. So here's each decade, the 2010s, which is already over. That's why this one's grayed out, but you can see what happened in that decade. And then the 2020s, of course, we're getting closer, almost halfway through, but that's green. So they're going to enter the change for the 2020s, the 2030s, 2040s, 2050s, and 2060s. And you can see these red tiles, that's no coal after 2035, and then all fossil fuels after 2040. Here, well, maybe I will show, actually, I'm not. Hydro, you can see it's land use. It does have a big land impact. Its reliability is quite high, but it's out of a scale of 5. But again, during drought years, the electricity produced is a little bit lower. The climate impact, there is some, methane released. So it is renewable, but it's not quite 1. It does have a climate impact. And then lifetime cost, relatively speaking, they're have a high initial cost and then lower maintenance. And then the max mix is 43. Oregon has dammed up most of the rivers that are dammable to produce electricity. So you can never go above 43. And then the max change, how much you can change in a given decade. And largely for hydro, it's 0 because really people talk now about dam removal. But in any case, we could see wind. Wind has a land use of 4, a climate impact of 1, a cost of 3, right? They have a limited lifespan, so you do have to replace them. A reliability of just 2. So now I want to hop down to constraints. These are a thumbs up, thumbs down. You don't have a plan unless you have all thumbs up. You have to supply enough power in your plan. Otherwise, it's not a plan. So that first line is the energy check. And then the second line is the growth check that you can't change too much. The third line is that reliability check, and it needs to stay above 3. So if you put in a lot of wind at reliability 2, you will actually get a thumbs down. So of course, you have to have a good energy mix. And one of the things to offset solar and wind is energy storage, because that has a reliability of 5. So you can see if you mix in wind, solar, and energy storage, you'll be just fine. Okay, and then we have those criteria, which are those on a sliding scale of unhappy, crying emoji, right? Climate, people are very unhappy about. So that's that crying emoji, unhappy, and up to happy. And so students have to work on their energy mix over the 50 years to try to get all happy faces and further prioritized. This is strongly called out for in the evidence statements, the performance expectations, evidence statements, that yes, all 3 of these are important, but of the 3, which one are you going to prioritize? Because someone that prioritizes environment is going to come up with a different plan than someone that prioritizes the climate. And that's really cool. I mean, this is one of the cool things, is that almost every student has a slightly different plan, because there's just a lot varying here. I'm just doing a time check. I'm gonna make a copy and just demonstrate putting in some variables here. And I know it's what size, and it would be so nice if we could fit this on a screen, but it's unavoidable. We'd have to make everything so small. So in any case, you do have to do a little bit of scrolling up and scrolling down. So I'll just quick say that, all right, I see I got to get off fossil fuels. So I actually, since I've done this before, I'm going to go coal. I'm at 32 and I want to get down as much as I can. I'm just going to put in down, I'm going to get off half of my coal. So I'll do -16. Uh-oh, but look at that. I'm only providing 89 power and I need to provide 110. Okay, so I want to grow my wind. I'm going to put in, let's just say I try to do 16. Oh, I got the red box. Why? Oh, because the most I can grow wind in this decade is just 12. Okay, so now I got my green box and I'm up to 101. I'm thinking ahead, so I'm going to start with energy storage too. The max is 5, so I'll do 5. And now I'm doing pretty good. 106, I got to do 110. Uh-oh, but I also got to get off natural gas. However, I got to think about this. Natural gas is better than coal, so I'm going to actually up my coal to -20. Okay, but now I'm back to 102. So you can just see, okay, I'm going to grow my solar then. I'll grow at 10. Oh, I'm 112 and I only need 110. Okay, well, I can back off solar, or I have 2 extra. I'm going to drop coal by 2. Okay. And so I'm done with the 2020s. I got thumbs up, thumbs up, thumbs up. Now, people are still pretty unhappy with me. And this is really good. Students want to make a super smiley face by the end of the 2020s, and that's not possible. You got to go into the 2030s and into the future. This is more than a 5-year problem. Okay, well, I know I got to be off fossil fuels. So I'm going to do -10 and -17. Okay, so I got off fossil fuels and I can see, let's see, I need to get 7, I got what? 1732 that I need. 59. I'm not going to get there. So I got to go and get off more fossil fuels. I can change by 6 more. So I could take 3 more away from coal. But of course, now I need that. I need to construct that somewhere. I could use wave technology, geothermal. I'm just going to do waves. Waves are really expensive, but I like it, so I'm just going to pick it. Okay, then now I'm -3 on coal. That I don't need -10. I only need -7 because I got off some. Okay, all right, so you kind of see the game. And students go through and do this. And these 2 decades are the hardest. And that's really predicted to be true, that the most change in the energy sector is going to happen in the next 15 years. Okay, but after this, it really calms down. They end up only changing little bits for the next 3 decades. But there's kind of a sneak peek at what we're talking about with computational thinking. I was using my brain and the computer rapidly calculating and giving me feedback. And I didn't really show that. It's really beautiful at the end. I wish maybe, oh yeah, we don't have the key open. But I do want to, and the beautiful thing about the teacher calendar is it makes this stuff quick, defined, and then I'm getting ready to hand it over to you, Matt, just to round out some of these last details and talk about the plan. But I just want to show the key quick to finish up this thought. It's really nice that at the end, students make their plan, and again, they try to get smiley faces is a minimum and a super smiley for their prioritized. And then something we added 2 years ago and then released last year was the overall score. It adds up all 3. And students don't have to, you could have a minimum of what they have to get to. And that's all we have, because students will turn this into a competition and they'll micro analyze. It's super cool. Students figure out that if they remove some of the dams, they can get an even better score. It produces so much good conversation, so much positive feedback. A teacher or 2 has even gotten pulled in and tried to do it. And then we didn't show it, but during the wind turbine, we introduced another type of graph. And if you look at this, it's called a Sankey diagram. But in any case, I can't show it very well, but really this is a energy bar chart stretched over time. And so you can just see at the 2010s, if you just look at this first slice, that's the energy bar chart. 40% was hydro. And then of course, by the 2060s, it just shows the energy mix. So students make this for their 50-year energy plan, and they include it in their engineering portfolio. And again, they will use the big ideas of science to explain phenomena and solve problems. So here it is. And with that, I'll turn it over to Matt to just say anything about the computational thinking and then bring us home with the final assessment.
Yeah, thanks, Bradford. So just a few things with the computational thinking. It does take students a little bit of time and playing with, and we encourage that. Like, we give them a lot of time. Some students might have all thumbs up by the end of the first day. Lots of students aren't there, and that is super important. We're walking around having conversations. The students who are talking about removing dams, yeah, like that's a good conversation to have because that actually is happening. So we really want this to be engaging, but we also want to support students in their writing and their thinking from that. So Bradford, if you could click on the next tab to the right there. And will you just zoom in, not on the section down below, but like zoom in right there. So we mentioned at the beginning, this 4-paragraph essay, and it's done with intent, and it's also done over time. It's not done just all at the end. So for example, the red lines there, exploring our engineering challenge, their claim, that was done on the 3rd or 4th day, where students are introduced to the problem that we were trying to solve, the 50-year energy plan, describing the constraints, the criteria, making a claim, and saying what might happen if the plan's not implemented. So they have a framework. So many students choose climate impact or environmental impact, cost. They choose one of those 3 things. And if a student is struggling, have them go, actually, we always do have them go reread their claim from the beginning of the unit and choose things that maximize what they already said was their priority. The second section, which says evaluating the 50-year plans, that evidence section is really just describing their plan and a competing plan, a partner, a neighbor, somebody else in the room. And it's just evaluating them, what they do, what was the strategy, what were their strengths and weaknesses. the reasoning about the best design is there's no critique, there's no like extra points for one student doing better. It is okay for them to say that their competitor did a better job. And they're just talking about the strengths and weaknesses and concluding which plan is better and why. So it's nothing against them for doing maybe a different plan or worse, choosing their partners. They're explaining which plan is better and why. And then the final last one is just like, what are the limitations? What challenges might happen? What problems might still remain? All of those are there and color coordinated and kind of brought together to that. One more support page, if you click to one more tab over, there's of course writing supports here. This is one of the best things that we do. I like to actually have them turn it in like in class, have an extra monitor, I read it, give them feedback right away from the rubric and have them go improve, edit. It's a really productive conversations, but not worth looking at in depth here. But if you just kind of scroll through, every single one of those parts of that essay have structure to it, provided structure and sentence frames that you can give them. So depending on your class, you may give them just the structure, or you may give them the structure with the sentence frames. It's a very powerful conversation that we have to support students writing. We really want them to this to feel like a culminating thing towards the end of the year. But we are running pretty short here on time. Is there any last words that any last things you want to mention before we close out here?
Nope. And I checked the idea capture tool. It looks like we got all the questions answered. It wasn't a lot of questions. So just that you can see how much good stuff there is in here. So just think about where you are right now in class. And if you're in unit 4, there's a chance you might want to cut out major pieces of unit 4 so that you do have time for unit 5, waves and technology. And then especially this unit right here that we're talking about, probably one of the most important units in the class. And you can just see there's a lot of really great engagement and rigor that students are learning high-level physics, earth science, engineering in an engaging way, and something that they think is relevant to their future.
Yeah, so I pasted the exit ticket. I'm going to go ahead, pause or stop the recording. And at the end of our webinars, we'll stick around for a little bit. Let me stop this.